This lecture is Introduction to Graph Part 2. In Part 1 of the Introduction to Graph, we talked about the properties and looked at graph as a mathematical and logical model. In this part, we'll look at some of the applications in a real-world scenarios of graph data structure. Okay, let's get started. A graph with all edges is called a directed graph, and a graph with all undirected edges is called an undirected graph. Usually, if the graph is directed, we explicitly say that it is a directed graph. So these are the two types of graph. Directed graph with edges are unidirectional or ordered pairs, and undirected graph in which the edges are bidirectional or unordered pairs. Now, many real-world systems and problems can be modeled using a graph. Graphs can be used to represent any collection of objects having some kind of pairwise relationship. Let's have a look at some of the interesting examples. A social network, like Facebook, can represent it as an undirected graph. A user would be a node in the graph, and if two users are friends, there would be an edge connecting them. A real social network would have millions of nodes. I only have a few in my diagram here because I'm short of space. Now, a social network is an undirected graph because friendship is a mutual relationship. If I'm your friend, you're my friend too. So connections have to be two-way. Now, once a system is modeled as a graph, a lot of problems can be solved by applying standard algorithms in graph theory. Like here in this social network, let's say we want to do something like suggest friends to a user. Let's say we want to suggest some connections to Mike. One possible approach to do so can be suggesting friends of friends who are not connected already. Mike has 3 friends, Ella, Bob, and Kate, and friends of these 3 that are not already connected can be suggested. There is no friends of Ella that isn't already connected. Bob, however, has 3 friends, Tom, Sam, and Lee, that are not friends with Mike, so they can be suggested. Katie has 2 friends, John and Lee, that are not connected to Mike. We have counted Lee already, so in all we can suggest these 4 users to Mike. Now, even though we describe this problem in context of a social network, this is a standard graph problem. The problem here is pure graph terms is finding all nodes having length of shortest path from a given node equal to 2. Standard algorithms can be applied to solve this problem. Just know that the problem we saw in social network is a standard graph problem. Okay, so a social network like Facebook is an undirected graph. Now let's have a look at another example. Sometimes in a graph, all connections cannot be treated as equal. Some connections can be preferable to others. Like, for example, we can represent an inner-city road network that is highways and freeways between cities as an undirected graph. I'm assuming that all highways would be bidirectional. Now, clearly we cannot treat all connections as equal here. Roads would be of different lengths, and to perform a lot of tasks, to solve a lot of problems, we need to take length of roads into account. In such cases, we can add some weight or cost with every edge. We label the edges with their weights. In this case, weight can be the length of the roads. What I'll do here, I'll just label these edges with some values or lengths. Let's say these values are in kilometers. And now the edges of this graph are weighted, and this graph can be called a weighted graph. Let's say in this graph, we want to pick the best route from city A to city D. Have a look at these 4 possible routes. I'm showing them in different colors. Now, if I was treating all edges as equal, I would say that the green route through B and C and the red route through E and F are equally good. Both of these paths have 3 edges, and the route through E is best. We have only 2 edges in this path. But with different weights assigned to the connections, I need to add the weights of the edges in the path to calculate total cost. When I'm taking weight into account, the best route is B and C. Connections have different weights, and it is important in this graph. Actually, we can look at all graphs as weighted graphs. An unweighted graph can be seen as a weighted graph where all weights of all the edges is the same. Typically, we assume the weight as 1. Okay, so we have represented an intercity road network as a weighted undirected graph. Social network as an unweighted undirected graph. We can represent an undirected graph as directed. We simply put 2 directed edges between each node. We cannot redraw a directed graph as undirected. Okay, this is good for an introduction to graph. So this is it for this lesson. Until next time, see you.